This is one sample that the one coal sample that you sent me. So I have the results. We have the small data windows and we have large data windows. With the large data windows, we can tell, look at different regions of the population and see how many particles and what percent of everything, the D10, D50, D90, D75, and we can print all these things. But generally what I try to do, the first thing I try to do whenever I finish a result, and this is just size, we can look at all the different shape measures. We have size histogram, we have a circularity histogram, we have a smoothness histogram, many other ones as well. And what I tend to do when I run an analysis, the first thing I do is I explain it to a customer what these different measures mean. To do that, the software has a diagnostic tool that has these shape test images. These shape test images allow you to get a better understanding how the particle insight works. So what we can do is look at any one of the shape measures, in this case equivalent circular area diameter, and we can see how it assumes particles are spherical. And in the case of these coal samples, which we'll see they're very irregular, assuming they're round is not going to be a good assumption. There are circularity measures which are independent of size, so one being very round. These particles were not round at all. They were very irregular that we ran your data. And then there's other values, for example, smoothness as well. They were not very smooth at all. So I use this quite a bit just to show customers how the different shape measures are created for actual particles. The first thing I'll always do is I'll go into post-run processing, and then the first thing I'll do is I'll look at the thumbnail images. The thumbnail images give me an idea of all the particles. There were 15,000 particles, and as we scroll through, we can tell that there were very irregular particles in the sample. But we could also tell there were two distributions in the particle. This was a calibration bead actually that was used, so it was one or two particles left over from a calibration standard. But as we go through, we can actually look at the different samples and see what the results are. We could look at how they look versus circularity. We could do many different things. So with respect to just looking at the actual particles, we can go through every single particle. If we only want to look at particles, let's say that are very irregular, or we want to look at particles, let's say that have a circularity greater than 0.7, we can actually go in and say only show me the particles that have a circularity greater than 0.7, and you can actually go here and then just see them, and then you'll look at the particles that had a circularity only greater than 0.7, and we can see that some are these calibration beads, but some are some slightly out of focus particles, but that can be eliminated and corrected. If we look at some of the other measures that we want to find, for example, if we clear that measurement, we can look at particles that were just had a very low, let's say the very low smoothness. Let's say a smoothness less than 4. We can look at the smoothness, let's say from 0 to 0.4. We can look at just that area of thumbnails. And obviously these are not very smooth, and those are the ones that have the very low smoothness. So we can clearly look at just portions of the distribution based on the different shapes of the particles. Other nice features of the particle insight is we have a percentiles area. Percentiles is really something for quality control, where the customer can actually put in quality control measures, the administrator, and be able to determine what would pass and what would fail. We have the thumbnail images, and when we hit thumbnail images, we'll see all the thumbnails unless there are limits applied. We also have something that's very interesting, which is a correlation plot. The correlation plot allows you to compare any two measures against each other. So let's say if we are assuming maybe we want to see how, if the larger particles are smoother, or we can compare size, ECA diameter, to smoothness. And we can see that there's something strange going on here, but we can see that there are definitely two populations with size and smoothness. So we see here in size, this is actually very interesting. Here in size, there are two distinct populations. There were some very small particles, by the way, below 3 microns. And there were a few big particles, very large particles. The way we can see the large particles is by volume and not a number weighted distribution. But we can see that there's two different populations, and this would be the population here, and this population would be this population here. We can see that the smaller population, this population here, had a more irregular shape than this large population, which I found interesting because normally when particles are getting smaller, they get smoother. This leads me to believe that this is a milling process and these particles do not dissolve over time. So the larger particles definitely are a bit smoother than the smaller particles, which is interesting. That's how you do the correlation plots. You can again look at, let's say, by circularity, and look at how they compare by circularity. So any two of the measures. Particle classification is something that allows us to actually set ranges to look at just if there are two samples, two populations in the sample. By doing that, we can actually go in and we can actually just look at, let's say we want to call this, I don't know, let's call it the small and the large. And we'll say that the smaller ones are the particles less than 10, so minimum of 3 to 10. And the large being 10 to 500. There's other measures we could put in here. So let's say we wanted to put a classification based on other measures as well, not just small and large that they smooth. But just to give you an idea how classification works, we end up coming back here and we could see that we classified 4,737 small particles, which is this % of the distribution, and these are the large particles. If we want to see more information, so for example, if we wanted to look at only the statistics only of the small particles, we can actually then just go here, and then we'll see only the graphical statistics. Let me close this. See, we're only looking at the small particles, but now we're only looking at the smoothness of the smaller particles, the circularity of the smaller particles, and all of these shape measures are represented only by the smaller particles. So if I go back and I just reopen the file, everything will come back to normal, and I could do the same thing here. Okay, and then I could look at for the large particles. Also, if I only wanted to look at the large particles, but then I didn't want to see the statistics, I want to see the thumbnails, I can go in and just look at the particles that had. Oh, let me get rid of this table. This table will actually show every shape measure, every measure for each one of the particles on the screen. Let me do this. Let me close this, and instead of putting all measures, I just want to see the size. It would be the value. I could look at thumbnails, and then it'll show me the size next to every particle. So these would be all the large particles. So that's how particle classification works, which is a very unique feature to the Particle Insight. Another nice feature that I found very interesting is actually we could do multiple run summaries. So for example, I ran this sample and then I ran this sample. I can do an overlay. I actually ran this sample, and I actually ran this sample differently. I actually changed the parameter just to be able to do a different overlay. And we'll see that I can actually, oops, oh, I'm sorry. It's this one and this one, but then I created this one just to do a comparison. This window comes up and we can actually look at, let's say, size, mean size by number, and we could do overlays. Obviously, the two samples that were correct were correct. This sample, this green one, is incorrect. I did this on purpose to show a difference. But basically, we could look at overlays not only by size, but we can look at overlays by any shape measure. If we want to compare circularity, we can see that that third particle had some similar circularity, and, but the size was very different. It was a different sample smoothness as well. We could look at comparisons for smoothness. So overlays are very useful. Okay, thank you very much.